technical stuff, and the one what I saw for the questions are looking for. So welcome, and now is your turn.
Well, thanks for your presentation. I'm waiting for my slides to come up. Well, just to keep this interesting, we'll have a little game with the audience. But okay, before I get there, let me first introduce myself. My name is Aldev. I'm the CTO and co-founder of MammothDB, one of our co-founders. I have about 17 years in analytics, data warehousing, and BI. And the reason I put it as various shades of analytics and so on is that I don't have a precise number, just an estimate. What I've mostly done in my career is sit between business and IT and get them to talk to one another. And currently, I'm in a very nerdy place. I try to make what other people call big data a bit more practical and usable. Okay. I got it. So a bit of a spoiler how this talk is going to go. We'll speak a bit about how big data tools are architected today and what their evolutionary path was in the past few years. We'll talk about the business environment that we'll hopefully try to survive in, and then we'll try to do a bit of forward thinking and try to predict what the future architecture is. And of course, I'm going to give you the answer because with big data, at least in my opinion, we're seeing something that's happened 50 years ago, so we're pretty sure what's coming next. Because, well, obviously, I think of myself as somebody representing that future. We'll look at some examples of using our product. And interestingly, Asperus won't be one of them. Okay, so there's the challenge. Spoiler alert, this will give you a feel of what I'm going to talk about and where I'm getting. So this is a challenge for the audience. Can you tell me how many Z's are in this soup? And we'll start doing that the big data way. And more accurately in the big data tool way. So let's divide the audience in the 1, 2, 3, 4. That's what we do, we partition the data. So let's take the first 6 rows to the one on my left, your right. Then 2, and then 3, and then 4. And anybody give me a guess? I'll aggregate. Your group?
15.
Is that the total or the?
The total is 15, so for us it would be like 4.
Okay, 4 from here. Anybody?
1/4 in our piece.
1/4.
In our piece.
So that's 4 and a quarter. And then somebody from number 2. Well, take that as a 0. Okay. And number 3, any guesses? Sorry? 26? Can somebody give me
1.6?
1.6? So that was 4.25 plus 1.6. That's 6 point something. Right? Okay. Good estimate. Let's try to do it the easier way. Let's see if this helps. So what I'm getting at is that the current data tooling essentially isn't very good at optimizing things and putting them in order. And where we're going is into more order. And Well, because I've been saying big data and big data and big data, let's try to think what big data is. I mean, the definition that I find very useful is that big data is where we see data sets that are pretty big in terms of size, and or complex, so that we can just throw an Oracle or MySQL and analyze them. So kind of, this is where our traditional tooling and technology fails us. So part of solving a big data problem is solving the big problem first and then the data problem. And some examples, like indexing hundreds of petabytes of web crawl content. This is both enormous and very poorly structured. So, I mean, that's pretty obvious as big data. Then if you have 10 million clients online and you want to provide them personalized analytics, what their activity was in the past month, how many friends they got, how many new connections, stuff like that. You've all seen it. That sounds like big data. Any other examples from your experience? Somebody wants to volunteer? Come on, people, you know what big data is. Anyone? Okay, I wasn't expecting no response at all, but it's relevant. Like, I mean, the stuff that I gave is, I mean, we kind of all agree it's big data, but I mean, have you ever tried to make a copy of an external hard drive that's 1 terabyte that you have filled in? Any guess as to how much time that takes? A couple of hours. I mean, if you're lucky, if nothing fast. So that's a pretty sizable problem, and that's just copying the data, not doing anything with it. And if you look at the business problems that companies are facing, they don't run into the petabytes. They often don't run even into terabytes. But I mean, you can try to run a query that does a full table scan with a few joins, say on a 100 gigs table in MySQL, and I think you will start feeling what big data is. It takes forever. I mean, if you haven't done the proper indexing, if you haven't structured it, it is challenging. Okay, and when we talk about the big data tooling, there is one predominant actor in this scenery. We're mostly talking about Hadoop. These guys are so much dominating the landscape that, I mean, every time I talk to somebody, they give me the, how are you compared to Hadoop this and Hadoop that. I mean, they never ask me the more relevant question of how do you compare against Oracle or Teradata. I get the Hadoop. And even though there are other tools, when we talk about analytics, most people understand the big data tool set, the stuff that you are going to start your project with as to be Hadoop exclusively. So we'll more or less talk about the Hadoop architecture before I turn to the future, because that's very representative of at least what's publicly available. I'm pretty sure the guys at Google are doing neater stuff than we see here, but we don't have access to that. Okay, so this is what Hadoop looks on the inside. By the way, do you guys have anybody raise their hand who has touched Hadoop? Quite a few people. So anybody who has been enamored by the performance and the quality of the tool? Not many hands? I wonder. Okay. So it all starts with a cluster of commodity servers. These are supposed to be pretty cheap machines that are reasonably good, not like very cheap stuff, but if you think about 2 to 5K range. That's the kind of stuff that Hadoop is supposed to run on. And then on top of these servers, you have a distributed file system. And what this guy does is it lets you store files, lots of them, and lots of very big files, files that potentially can exceed the capacity of a single hard drive. And then on top of the file system, there is a distributed compute component that lets you build programs and run queries, and a resource manager that says this part of the program is going to run on this CPU on this node. We have a NoSQL data store that one of the later speakers will talk about. And I'm not going to touch upon this one at all. And then we have, because the MapReduce, as you see a bit further, is not a very easy to use programming interface. We have higher level applications that we use to access the data, such as PIC, which is a data flow language. You not only tell it what data you need, but also how to process it, what the steps in getting stuff out are. And you have Hive that you use with something that resembles SQL. It's called HiveQL. It's a declarative language that you can write queries in. And then you have various other more advanced extensions like machine learning and data mining that's not on the picture. Okay, so let's look at how the file system does its thing. So essentially we have big files. Imagine these are files that run in the terabyte range. What the distributed file system does is it breaks them into pieces, the so-called blocks, and it spreads the pieces around the infrastructure. So you have piece number 1 sitting on one of the data nodes, piece number 2 sitting on another data node, piece number 3 sitting somewhere else. What happens is that if you have several clients writing or reading, they access directly the data nodes. And this way you actually don't hit any bottlenecks on the data node, because client 1 is accessing one, whereas client 2 is accessing another. And the combined bandwidth and throughput is much higher than can be achieved, say, on a network attached storage, where a single node is somehow constrained by its network interface or another component. And actually, this works out very well. It scales linearly. If you run out of space, you just put in more nodes or to put more blocks. You can monitor the infrastructure, evaluate when it reaches a certain percentage. It's really scalable. You can put big files there, you can put quite a lot of files there. One other feature of these systems, because when you have lots of servers, they start failing. And I've seen one of the Facebook famous 3,000 node cluster pictures, and you see that every day between 1 and 10 nodes will fail. In a month they will be replacing. So there has to be some mechanism of recovery. And what these guys do is pretty simple. Whenever a block is stored somewhere, it is also replicated on some of the other nodes. So if one of the nodes goes down, then you have a spare copy somewhere else in the system. And while the system detects there's a node that's failed, it will again do the replication to make sure there's enough copies. So in terms of throughput, scalability, and tolerance, this is a pretty good design. It works well. now we go to the classical workflow of how a compute task executes on Hadoop. This is all done through a MapReduce programming model that I'm not going to go into the details, other than saying that it essentially consists of a map phase where you get the raw file and you apply some logic to get the structure from that raw file. It starts out as unstructured, goes through structuring to extracting content, and then it gets stored on the local file system, and then it gets shuffled, which essentially means moved to somewhere else on the system, on another node, in order to be aggregated. And finally, the output of a single MapReduce job is that it gets written back to the distributed file system. So if you count the number of file accesses that you have, you start out reading the file, interpreting it, then storing it locally, sending it through the network, then doing some additional logic, and then storing it back to the distributed file system. And the MapReduce, a single MapReduce job is a pretty simple beast. You can't achieve much. So usually when you fire a query through a high-level language type, what happens is a graph like that is executed with multiple MapReduce jobs, and each of them takes a file, reads it, stores it locally, sends it across the network, and so on, stores it to the file system. This happens at every stage, so that's pretty inefficient. And in terms of programmability, I mean, the classical Hadoop gives you a MapReduce, which are basically two functions where you're more or less free to do whatever you please as an application programmer. However, I mean, then being simple and flexible means that there are lots of these jobs that you need to string together to do anything useful. And well, the biggest difficulties with MapReduce is if you need data from two files that you need to join in order to report them side by side. Well, joins are difficult because the same key on which you join may be sitting because the file system just distributes blocks by the file, by block size. It doesn't care about the contents. I mean, they have to be sent somewhere else over the network in order to be joined. And then you have the problem of a specific query that's pretty difficult as well because you need to scan the whole file to get what you are interested in. So in terms of resource, essentially one of these phases that I was talking about, maps for reduce, essentially you have the correlation that one of these guys runs on one core in the system. So if you have a pretty sizable cluster of 100 nodes times 4 cores each, like the theoretical throughput on a map job that you get is about 15 gigabytes per second. That's it. I mean, if every one of the 100 nodes is running at full capacity. However, I mean, in reality, when you take the whole execution framework, that becomes mere 2.5 theoretical gigabytes per second on a 100 node cluster. But if you scale that down, actually it becomes much worse. It becomes less than this 128 megabytes per second is less than your hard write can do. So the cluster as a whole running classical Hadoop with 5 nodes isn't that exciting. And another thing that having so few cores does is that when you try to run concurrent jobs, they can compete heavily for resources. So concurrency isn't great. I mean, if you have 400 cores, they can serve at any one time 400 tasks that are each processing about 40 to 64 megabytes at the same time, which is about 12 gigabytes being processed at any one time. It's not that much. If somebody else has a file with another 12 gigabytes, they sit in a queue and wait. Okay, so moving on to the new kid on the block part, that's very sexy, that's the new optimized execution framework. So it more or less goes through the same logic. There is it sits on a cluster of commodity servers. It does the distributed file store, which happens to be the same, the HDFS. Then we have a distributed compute component that does quite a few optimizations and a few higher level apps that let you write data flow applications in a programming language rather than big. And you have a query too. And what happened between classical Hadoop and Spark is that they came up with pipelines for jobs. So if you have string a few jobs where you don't need to move data between two consecutive map and reduces, this is optimized. There's no data movement. And not only that, but they're only also caching the intermediate results in memory so that they get reused. And this speeds things quite a lot. They have also provided a rich set of high-level language data flow operations like joins, group bytes, not just map and reduce, and support for popular languages, which makes it much easier to write code for Spark. Also a lot quicker than Hadoop. But still, what hasn't changed is, your basic workflow is scan the file, understand its structure because it's not structured when you store it, then perform analysis. And the whole philosophy, I've been repeating that a few times, the whole philosophy of big data tooling as it is now is you ingest and collect all the data as it comes. That's the primary objective, and then figure it out later. Analyze in your spare time. Other improvements that have happened in this field are, we have seen better formats than the plain text columnar storage that optimizes access to just what you need. We have seen lots of compression to reduce the data that's flowing between data stores and compute tasks. And we have seen a lot of SQL and Hadoop tools that essentially, to me, mean that people want to use a higher level declarative language to do their job rather than write scripts and scripts and scripts. Just access data and have the tool figured out. And we also have a number of very optimized C++ implementations. So let's look for a while at what an enterprise, typical enterprise does with this data and see if there's a fit. So a typical enterprise evolved to cover departmental functions. We think of ERP, billing system, quite a CRM, quite a few systems out there. And they have evolved more or less independently. Most of them are built the old way, using structured data and transactional data. If you want to do a report from both, then you have to align them. Typical challenges for these enterprises are get the data right, data quality. Oftentimes the data is user type, there are errors, there is misalignment between different data tools. Then the data integration. Data integration is probably the number one. It's making all the systems talk one language, having reports across functions. Then, they expect users, these enterprises expect to click and see their report within a reasonable time. Their audiences are business, they're not programmers. They expect to be able to give their customers a self-service analytics package where you can log into the website, get your reports, and not bother calling somebody to send them by email. And nowadays we're seeing significant volumes that, because the first challenges are pretty clear, there are tools to handle them. They're not cheap, but they're there. But the volumes are getting bigger, so the tools are getting more expensive. Next challenge is, I mean, these companies, most companies have something. They're not like starting out to me. And they have invested in their IT and training, so they want to leverage, for example, they bought columns or something. They want to leverage this investment. And well, budget means that they can't really afford to, most enterprises at least, that have 10 terabytes or so. I mean, they're not, most of them are not running into the billions of annual revenue. They can't buy terabyte. It's just a matter of fact. So they kind of are interested into can the big data technology help them? But this is what the big data tools of today offer them. So they offer them reliable and scalable storage for files. They offer them reliable and scalable benchmark computation. You fire a job, you wait. And they offer them a system that doesn't quite work when you're running with 5 nodes. So you have to run 100 to be reasonably efficient. And in terms of unified data integration, the approach of today's tooling is, well, the data is there, it's quality up to the user. I mean, whatever the user programs makes out from the data, that's level quality data. Its integration is up to the user. Again, whatever they program, that's how it works. And because our joints, did I mention they were difficult? I mean, integration is not very easy to do. I mean, if you have big data sets that you need to join plans and move on, that's hard. Which makes the user a very small group of very highly qualified data scientists that most companies don't have. They also offer a new programming interface and lots of cost to acquire, extend and run. I mean, I can give you the approximate cost of 100 node cluster at Amazon using M2X large. That's $500,000 a year. No bit. So Hadoop adoption basically is not great. Users, according to Gartner, the topmost uses are cloud storage, some basic analytics on single table, and proof of concepts. And for like the past 5 years, there's always been a large percentage of next year will do the advanced analytics. Clusters that are being used in practice are pretty small. I guess that's the budget constraint. And they don't really run a lot of storage. So that's the landscape that we are looking at. Top reasons they cite for slow adoption is lack of adequate skill, which is, to me, CIO speak for you don't have a clue. And they have no business case for using big data tools. And especially, I mean, if you look at Hadoop, what it's good for, batch processing, big data, big unstructured data on large infrastructure, but not that good at the other stuff that matters to business users. And, well, it kind of sounds familiar. 50 years ago, in the 50s, there were big mainframes that you had to wait for access to, that were centralized. Users were sitting in a queue waiting for their program to run, and programmers were responsible for writing code that will go through the records one by one, understand them, and write the queries. So we pretty much know what happened since the 50s. What happened is that we actually built an agreed on data management system that managed data. We call them PBMSs. We pretty much agreed that these will be optimized, that business users will get a query language that can easily interface downstream tools to do the data management and presentation. And we pretty much agreed that there is a right way to integrate your data. The one thing that we haven't agreed on yet is that scale out is a good idea, but it seems, well, from the current data, big data experience, that scale out is the way to go. And this is what we see as the future, future technology. I mean, we'll have more or less the same stack, but instead of running, well, compute on files, we'll have an integrated distributed database engine that knows how to do joins and how to do optimized query. We'll have a distributed framework to run it and a declarative query language on which stuff runs. And pretty much this is what MammothDB is. We have built a system that is running a relational database for analytics on every node. It does SQL, so you cannot really tell it's something different. And when you look at how it is used, and this is a business case in logistics where we have built a predictive model, this looks like a very typical data warehouse. We get data from a client, we run a prediction model that does SQL against MammothDB, and then we have a number of front-end tools that run SQL against MammothDB. In terms of methodology, there is nothing specific. It's just that the data is really a lot and computation is pretty tough. Again, another use case, same thing. We have multiple data sources that we consolidate using standard SQL, and then we have SQL compliant tools running on top of it. And, well, sorry about taking a bit more time than needed. Thank you. And I guess I'll get my Q&A later on.
We have a lot of questions, but what we talk about to make at the end all the questions. So now we are just wondering, are you okay to make into the panel with all the questions? So if if you prefer now, he can answer on some of them, but we will have a luck with the time. So can you raise if you want questions now to be raised? Okay, so we will leave it for later on. Okay, so now is the time to present the next speaker.